So hi everyone, today we'll be discussing about what is matrix factorization and what are the different algorithms that can be used for matrix factorization. So before starting, matrix factorization is a very crucial concept in mathematics that find its application numerical place in numerous places. So for before starting, we must understand what is matrix factorization or matrix decomposition. So mathematically speaking, given a n cross m matrix where n is equal is total number of rows and m corresponds to total number of columns of the matrix. Using matrix factorization, we can decompose this matrix into multiple matrices of different dimensions, such that on matrix multiplication of these matrices, we again regain our original matrix. Now, where it finds its application, this mathematical concept, collaborative filtering for recommendations, it is one of the most important algorithms and most famous also. Dimension reduction, if you have read about PCA, you must remember that how we go for eigenvalue decomposition. That is one of the types of matrix factorization algorithms. Image compression, text mining, and whatnot. So there are multiple purposes for which matrix factorization can be used. So now, as we all know, what is matrix factorization? So we will now jump onto the different algorithms that we will be exploring in this vlog. The first algorithm that we will be exploring is LU decomposition. So LU decomposition is one of the most famous matrix factorization techniques, where L stands for lower triangular and U stands for upper triangular decomposition. So it gives you an idea ki what are the two matrices the original matrix get decomposed. So it got so the original matrix get decomposed into two matrices. One is of type lower triangular, another is a upper triangular. So if you want to know what is upper triangular or lower triangular matrix, you can see in this particular image. So in case of a lower triangular image, you can see that only the lower triangular values are filled, else everything is zero up in the upper triangular. Similarly, for an upper triangular matrix, you can see that all the values above the diagonal are non-zero, else everything below the diagonal of the matrix is zero. That is an upper triangular matrix. So how are we able to implement LU decomposition of over a given matrix? Using Gaussian elimination, or also called as row reduction. So what is Gaussian elimination slash row reduction? So basically it aims at converting a matrix into upper triangular matrix by applying linear row operations like row 2 equals to row 2 minus 3 into row 3, row 1 equals to row 1 plus row 2 divided by 5. So basically you are able to understand that we are trying to apply some linear transformation over some other row and subtracting or adding it to the different row. So in this way, we are converting a given matrix into a upper triangular matrix by applying multiple linear transformations. So we will now see one of the examples how a particular matrix can be LU decomposed. So assume that we have got this particular matrix A equals to 3 1 2 6 3 4 3 1 5. We'll be now initializing two matrices. One is L, that is an identity matrix. So if you don't know, identity matrix has every value 0 except diagonal. So diagonal has values 1, as you can see here, and U equals a copy of the actual matrix that we wish to decompose. So as A was this, so U equals to the actual matrix. Now we will try to convert U into a upper triangular matrix using Gaussian elimination. As I told you, we will use a combination of linear transformations to convert this U into an upper triangular matrix. As you can see that it is not upper triangular matrix right now, as the values below the diagonal are not 0. So basically we wish to convert 6 3 and 1, as you can see here, to 0. Then it will become a upper triangular matrix. So the operation that we will be performing are row 2 equals to row 2 minus 2 into row 1. So as you can see that row 2 is 6 3 4. Once I am subtracting minus 2 into row 1, what we would be getting? 2 into 3 becomes 6. Hence, if I am subtracting 2 into row 1, this particular value becomes 0. Right? Eventually, when we are doing 2, when we are subtracting the whole row, this value becomes 1, and this particular value also becomes 0. Now, once we are performing this first operation, the multiplier used with the other row is 2. So, and which value we are trying to convert to, which particular value we are using this multiplier to convert to 0, that is u21, second row first column, right? So eventually L21 becomes equals to 2. This is the logic. So eventually we'll be converting u into a upper triangular matrix, and whatever multiplier that we're using for a particular position, on that particular position we will be placing that multiplier in the L matrix also. Now similarly, row 3 equals to row 3 minus 1 into row 1. So as you can see that for converting this particular, as I told you that to convert u into a upper triangular matrix, we need to convert three values into 0. This one and this one. So by the first transformation, we have converted 6 into a 0. The second transformation will convert 3 into a 0. So it is nothing but row 3 minus row 1 because the values are same. So the multiplier uses 1. Now do remember that we are just not applying the transformation of a particular value but on the whole row. So this value becomes 0 but other values will also change, right? So the multiplier uses 1 to convert u31 equals to 0, hence L31 equals to 1. So after two operations, we have got this L equals to L00210101, u equals to 312010003. You got my point because we have applied two operations on one on row 2, other on row 3. Similarly, the two multipliers that we have used is 2, which is placed here, and the 1, which is placed here. Now remaining this particular point, but it is actually already 0. If that is the case, then the multiplier that we would be using for any transformation would be 0, right? You can multiply it with anything, it will become a 0 only. So in that case, this value remains 0 only. So now all the three values in our upper triangular matrix has become 0. So eventually the transformation LU decomposition has been done and the actual matrix has been decomposed into two matrices. L equals to 100210101, U equals to 31210100003. If this particularly won't have become a 0, why this value has become a 0? If I have because I have performed this operation, row 3 equals to row 3 minus 1 into row 1. So this value also became 0, this value also became 0 automatically because the second element was 1. It is by chance, it is not intentionally. So if there were having some other values such as 2, for example, this value won't have become a 0 after the second operation, and we need to again perform a third operation to convert this particular value also a 0, right? So in this way we are able to do a LU decomposition. If you try to multiply L into U using matrix multiplication, you will be able to get your actual A. You can try that out. It will be successful. So next algorithm for matrix decomposition that we'll be discussing is QR decomposition. So this is not the same QR that you scan for getting items or payments, is something else. So as similar to LU decomposition where we are decomposing the matrix into two matrices, in QR decomposition also we will be decomposing it into two matrices. So one is the orthonormal matrix, another is the upper triangular matrix. So first of all, we'll try to understand what is an orthonormal matrix. So orthonormal matrix has two particular features. One is that all the column vectors present in the matrix are perpendicular to each other and each column vector has a length of 1. If the column vectors are mutually perpendicular to each other but are not of unit length, then it is called as an orthogonal matrix. Just remember this. Now I will be showing you how to perform a QR decomposition. So we will be first of all taking a matrix A, 1 4 7 2 5 8 3 6 9. We'll be initializing two matrices Q and R with zeros. Now we'll be performing Gram-Schmidt orthogonalization. So this is a big jargon. I think even I'm not able to pronounce it, how to pronounce this, but we'll be learning how to implement this orthogonalization. So basically it is a mathematical process used for transforming a set of linearly independent vectors, basically the columns of a matrix, into a new set of orthogonal perpendicular vectors, which means each vector is at a right angle to each other. So basically, as I told you, in case of a orthonormal matrix, orthonormal vector matrix, all the column vectors are perpendicular to each other. So first of all, we will be converting all the vectors perpendicular and then normalizing it to make it orthonormal. This is fine. So how we are able to perform this? The first vector v1 remains unchanged since there is no other vector to make it orthogonal to. Makes sense, right? Because it is the first vector, you can't make it perpendicular to anything. Once the second vector comes in, you need to make it perpendicular to the first vector v1. So we will be subtracting the projection of v2 onto v1 from v2 to make it orthogonal to v1, right? How a projection is calculated, I will show you. For the third vector v3, subtract the projection of v3 onto v1 and v2 both, because you now as you're moving ahead, you need to make it orthogonal to all the vectors present in the past, right? From v3 to make it orthogonal to both v1 and v2. Similarly, for fourth vector, for fifth vector, for sixth vector, we need to subtract the projection of that nth vector from its past vectors v1, v2, v2 till vn minus 1, and subtract it from v nth vector to make it orthogonal to all the previous transformed vectors, right? I will be showing you an example, so no need to worry, and don't get afraid by the mathematics explained here. Now this will convert them into orthogonal vector. As I told you, for orthonormal we will be normalizing that. That is only change. So let's get started. So we already have taken our first, we have taken our matrix A. If you have forgotten, this is the matrix 1 4 7 2 5 8 3 6 9. Now for first column of Q, that is Q1, we will be normalizing the first column of A. As I told you, for first vector V1, there is nothing to make it perpendicular to. We will be just normalizing it. So as you can see that V1 equals to 1, 1, 2, 3. We are calculating the magnitude of V1, 3.7574, and first column of Q, that is Q1, equals to V1 upon divided by 3.74, that is this 0.27, 0.53, 0.80. First column we have got. Now for the second column, 4, 5, 6, we first be subtracting the projection of V2 from V1 from V2. So here you can see that V2 minus V2 dot Q1, dot product we are calculating from Q1. Q1 is the first column that we have calculated for Q, which is already orthonormal now, into Q1. So the first one is a dot product, second one is a matrix multiplication. Do remember that. V2 is 5, 4, 5, 6 minus, we are calculating the dot product between V2 dot Q1. So V2 is nothing but second column of the actual matrix. And then eventually we are multiplying it with the first column of the Q matrix that we that we have calculated in the first step. So once we are able to get the projection V2 comma V1, which is 3.52, 4.1, 4.57, now the last step is to normalize this and then get our orthonormal vector for column 2. So this becomes a 0.5, 0.58, 0.65. Now going for the third one, because we have considered 3 cross 3 matrix, so we will be calculating projections from V3 to V1 like this: V3 minus V3 dot Q1 into Q1 minus V3 dot Q2 into Q2. As I told you, as we are moving ahead, we need to make it normal to all the existing orthonormal vectors also that we have already calculated. Again, the whole mathematics goes the same, and we get a final column for Q. Now, how to calculate R? We have calculated Q, but we haven't calculated R. So R again will follow a common strategy. As in the equation that we are getting, we are assuming that A equals to QR, because A is getting decomposed into two matrices, that is QR. So now in this equation, we know A, we know Q. So we can transfer Q to the other side of the equation, that is Q transpose. So Q transpose into A should give us R. So basically, using the calculated value for Q, we are able to calculate R also. So this is how QR decomposition is done. So the next algorithm for matrix decomposition that we'll be discussing is eigenvalue or spectral decomposition. So eigenvalue or spectral decomposition is also a very popular matrix decomposition algorithm that is used majorly in PCA. So if you have read principal component analysis during dimension reduction, eigenvalues and eigenvectors plays a very important role. So before moving ahead, we need to know a few baseline concepts which we will be using while performing eigenvalue decomposition. So what is an eigenvector? For a square matrix A, an eigenvector is a non-zero vector when multiplied by the matrix A, only changes in scale but retains a direction. And eigenvalues, the corresponding scale factor associated with the eigenvector is called the eigenvalue. So eigenvector and eigenvalues are basically related to directions of particular matrix, something a bit mathematical that I'm wishing to skip, because eventually I'm assuming while reading PCA, you must have read about eigenvalue decomposition, specifically eigenvalues and eigenvectors. Now, moving on to eigenvalue decomposition, the relationship between eigenvector, eigenvalues, and actual matrix is represented by this particular equation: A into V equals to lambda into V, right? Where lambda is the eigenvalue, V is the eigenvector, and A is the actual vector. Now, eventually, if we move this particular term on the right hand side to the left hand side, we get a minus, and we can take V as a common. So this becomes our whole equation: A minus lambda I. I is a identity matrix into V equals to 0. Now we will be using this particular equation to get eigenvalues and eigenvectors, right? So assume that we are taking this particular matrix for starting. A equals to 4 1 2 1 5 6 2 6 7. Now form the matrix A minus lambda I. So A minus lambda is equals to 4 minus lambda 1 2 1 5 minus lambda 6 2 6 7 minus lambda. So Why this is so? Because lambda is a scalar and I is an identity matrix. So in identity matrix, we have values only in the diagonal, 1, 1, 1, and rest of the values are 0. And hence, when we're subtracting, lambda is getting to only to the diagonal values of the matrix A. Now we will be calculating a determinant of matrix A minus lambda I. Now, determinant is something that has a different formula for different dimensions of matrix. For a 3 cross 3 matrix, this is the formula that we follow. A into EI minus FH minus B into DI minus FG plus C into DH minus EG. So we'll be applying this particular formula to get to a determinant equation for our particular matrix A minus lambda I. So we get this particular equation for determinant, and if we assume the determinant for this particular matrix is 0, we get an equation in terms of lambda. Now once we solve this particular equation for lambda, we will get our eigenvalues because lambda equals to eigenvalues. Now once we get our eigenvalues, we will be placing the different eigenvalues into this particular equation A minus lambda I into V that we created earlier, and we will be calculating V, and eventually we will get our eigenvectors also. So in this way, we will be getting RV, that is eigenvectors, that and hence helping us in the eigenvector decomposition. The next algorithm in matrix factorization that we'll be understanding is singular vector decomposition. So singular vector decomposition SVD is also a very popular technique for dimension reduction. So previous to singular vector decomposition, we have discussed LU decomposition that decomposes a matrix into two parts. After that, eigenvalue decomposition that decomposes a matrix into a scalar and a matrix. Now, in case of singular vector decomposition, we'll be decomposing the matrix into three parts. But before moving ahead towards the mathematics, we need to understand a couple of concepts, that is singular values, which is equal to the square root of eigenvalues, and singular vector, which are normalized eigenvectors. Normalized means unit length eigenvector. So, how to calculate eigenvalues and eigenvectors that I have discussed already in my explanation for eigenvalue decomposition. You can check that out. Now, SV decomposition is represented by A equals to U cross sigma cross V transpose, where U is left singular matrix, sigma is singular value matrix, which is a diagonal matrix. So basically, in a diagonal matrix, as I've already explained, only diagonal values are present, rest of the values are zero. So the singular values that we will be calculating for a matrix, we will be placing them on the diagonal and write singular vectors matrix for V. Though you don't need to worry, I will be explaining you how all these three are calculated. So starting off with SVD, this might be a bit tough on the mathematical side, so just pay attention. We will be first calculating A transpose cross A, and we will be calling it as A dash. Now we will be calculating the eigenvalues and eigenvector for A dash, which is very similar to eigenvalue decomposition that we have discussed earlier. In case of eigenvalue decomposition, we were calculating eigenvalues and eigenvector for A minus lambda I. Here we are calculating it for A transpose cross A. That is the only difference. Next, we will be calculating the singular values for A dash using the eigenvalues. As I told you that singular values are nothing but root of eigenvalues. So we will be calculating the singular values for eigenvalues, and we'll be placing those eigenvalues on the diagonal of a identity matrix, forming it sigma for us. So out of the three matrices, once we calculate singular values, we are able to get a sigma. Now we'll be calculating the singular vector for A dash by normalizing eigenvectors. So it is, again, as you can understand, it is an extension of eigenvalue decomposition only. So in case of eigenvalue decomposition, we're calculating eigenvalues and eigenvectors and using them in the final representation. In case of SVD, we are going one step ahead and we are calculating singular values and singular vectors. Now once we are able to calculate singular vectors, which is nothing but normalized eigenvectors, V is equals to matrix of singular vectors of A dash. Sigma is diagonal matrix with the distinct singular values. And for U, for calculating U, the third remaining matrix, we can use this particular equation, because in this equation we have four variables: A equals to U cross sigma cross V transpose. We know A, we know sigma, we know V transpose. So eventually, using this particular equation, U equals to A cross V cross sigma transpose, and we will be placing all these three values, we will be getting a U also. So in this way, SVD decomposition happens, where using singular values we are constructing our decomposed matrices. So the next algorithm that we will be discussing for matrix factorization is Cholesky decomposition. So this is very interesting because in all the previous matrix decomposition algorithms, we were either decomposing the matrix into two or three or four matrices, but in this case, we are decomposing it into a one matrix only. That is The formula that stands is A equals to L cross L transpose, where L is a lower triangular matrix. So basically, it is a very formula driven method. So I won't be jumping into the examples, but I will explain you how the formula is getting used. It is very weird formula. So the first element of L, that is the top element of the diagonal of L11, that is L11 equals to root of the first element of A. The first column of L, except the first element, we have already calculated the first element. So the remaining first column of L is filled using the first column of A divided by the first element of L, that is root of first element of A. It is completely mathematical. You just need to look into the formula and concentrate. You will get what I'm talking about. Else you might get confused. So talking about the diagonal elements, how the diagonal elements are getting set up. So the formula that is getting followed is root aii minus summation over lip whole square. So how it is calculated? So for example, if you are trying to calculate L33, so this becomes root a33 minus L31 square, L32 square, L31 square plus L32 square. That's it. So basically, all the previous elements of that particular column in L will be squared and then subtracted from the diagonal element of A. And the final is any other elements present in L, how to set them up. So basically, will be taking the actual element from A from that position minus all the previous elements from that particular row and all the previous element from that column. We will be calculating a product and then subtract.